Okay, I'm back here with the last video for this chapter, and we will discuss now the last part of it, which is 2.13, and it's Newton's law of gravity. So here I prepared a little bits of the information that I want to share with you guys, and the question here is, why do objects fall downwards? And to explain this, we're going to use the Newton's law of universal gravitation, and the way the law states, I'm going to read it to you, and after this we will be able to figure out why objects do fall. So the Newton's law of universal gravitation states that for the two particles separated by a distance r, so this is r, I just boxed it here so that you don't confuse it with some other term, the force of the attraction directed along the line joining the particles, I got two particles here, and there's this line in here, invisible line, is directly related to the masses and inversely proportional to the square of the distance between them. And of course, the distance that we are talking about here is the referring from the geometrical centers. I mean, some objects, if we're lucky, are spherical objects, and so all we have to do now to measure the distance r from the center of this object to the other center of the other object. But some of the objects, like human beings, for example, or some other objects, they don't have the spherical shape, so you will have to find the geometrical center of that shape. Now, how do we mathematically express now this statement that I just sounded here? And mathematically, you relate the two masses directly to the force of attraction here, or gravitational force, and it's inversely, guys, related to the distance between these two objects, like I just shown here. And what I forgot to do, I forgot to put this little r in here. Okay, now, distance squared. Now, the g here is the universal gravitational constant, and it's equal to 6.673 10 to negative 11 Newton times meter squared divided by kilogram square. And it was discovered by English scientist by the name of Henry Cavendish in 1798. He used a torsion balance to discover it. And again, for me to explain this number, how he discovered it, it has to be just a lecture in itself. So I'm going to, I'm not going to do it. It's goes beyond the scope, guys, of this course. But he did do the experimentation. He did discover this number. This universal gravitational constant is constant everywhere in the universe. It is the same value, and so it will be always given to you solving the problems. Now, what's important here again is that as long as you have these two masses, two particles having certain masses, they always have some force of attraction or gravitational force. But how come when we close to an Earth, let's say, we're interacting with different objects, how come we are not attracted to those objects? And the answer is very simple. If you take a look at the mass 1, mass 2, and you plug in, let's say, your mass and mass of the objects that you're near, you will see that the force of attraction will come to a very, very small value here. However, in the when I'm going to raise everything, I'm going to talk about the weight versus mass. You will see that when you were talking about now huge mass, let's say as Earth, and as big as Earth, now that force of attraction will be felt. And that's why the question was, why do objects fall downward? And the reason is because the Earth is a very, very big, has a very big mass. And what it does, it increases this force of attraction. And these two particles, well, in this case, huge Earth and whatever the object is trying to attract, or whatever the object near it, this object now feels this force of attraction, and it falls downward. Now, the question here as asked at times, what is the difference between the mass and the weight? And to answer this question, I have to state now, again, this equation, force of attraction, or gravitational force, is equal to G. Instead now, M1, I'm going to replace it M sub E, which is the mass of the Earth, times some object's mass, it could be a human being, divided by the R squared. Now, so we can replace now this force of attraction here by W, which will just stand for the weight of an object, and G times, again, M sub E times M divided by R squared. And so now you can see, guys, that, and remember we learned before the second law of Newton is, let me just put it here, M times A, which was, in this case, M times G. And so what's interesting here now, if you compare now these two equations, you got the mass here and the mass here, and of course these two masses are constant. These are the masses of the object that is being attracted by the Earth. But what does change, this mass of the other object, in this case is Earth, and the distance between the center of the Earth and the center of the other object. Now, so this component now, I'm going to have to include this, even though it's a constant here. But this, when you take these three terms, this is what the G will be equal to. G is equal to G times M sub E divided by R squared. So if you plug now the G that I already gave you guys, the value for this constant, the mass of the Earth, you can get it from the textbook. It's in the chapter 2.13, part of the chapter. And the radius of the Earth squared, you will, guys, get 9.80 meter over second square, your acceleration due to gravity. Now, but what happens now to the weight when you travel to the moon? So let me just replace now, instead of M sub E, you're going to have M sub M times mass, could be U here, divided by R squared. Now, the weight now will change when you go to the moon, because the mass of the moon will be different than the mass of the Earth. It's obvious. Earth is much bigger, the mass of the moon is much smaller, and so your weight on the moon, guys, would be much smaller by 6 times now. So if we can do this calculation, we can plug the numbers in and work this number around, but you know, it's a simple mathematics here. Now, so in other words, when you're standing on the moon, I mean, not on the moon, on the Earth here, let's say, this is your Earth here, this is the radius of the Earth, and this is some object, let's say, and of course is being now pulled in here by force of gravity here, and we got this distance here, R, and this same object, let's say, on the moon, which is much smaller now, the radius here, of course, for the moon, the radius R sub moon is smaller also. However, the mass is much smaller than the Earth mass. And what's going to happen, let me put this object here, is being pulled by some force of gravity. So even though the R is also smaller here, meaning that this is bigger. However, the mass of the moon is drastically smaller than the mass of the Earth. So this factor here is important here, and that's the factor that will change your weight on the moon by 6 times because of this disparity in the masses between the moon and the Earth. But what will stay the same on the Earth and the moon is your mass here. And this is the moon, and let me go to your Earth here. There it is. See, that doesn't change. This is constant. This is constant. Again, what's changing is these two parameters here, these two terms. This stays the same, But if you want to calculate now the acceleration due to gravity on the moon, you will have to say g is equal to g times the mass of the moon divided by the radius of the moon squared. And that's how you're going to get the acceleration due to gravity on the moon. And that should be 6 times less than the acceleration that is on the Earth.